Hello again, it's your friendly heavy physics teacher, and this is my online lesson for my Regents Physics class, Unit 10, Lesson 1.2 and Lesson 2. Okay, we're going to finish up talking about magnetism, magnetic fields, and then we're going to introduce electromagnetism. All right, so that's what's on tap for this lesson today. As you may have experienced in playing with magnets on your own, you realize that magnets don't have to be in contact in order for them to exert a magnetic force on each other. Okay? So, anytime you can have a magnetic material and it influences another material nearby it magnetically, we call that area in which that magnetism is interacting, we call that a magnetic field. The other way to think about it is if you have a bar magnet and it's just out there in space and you know that it can exert a magnetic force around it, then the region around it we call a magnetic field. All right. So in a lot of ways, this is very similar to what we use to describe the electric field and the gravitational field. Now, with the electric field, we talked about electric field lines or lines of electric force. Magnetism, we talk about flux lines or lines of magnetic force. All right. Um, uh, and this is because the magnetic field was often thought of as something that would cause a change. And flux is another word for something being in transition, something changing. Okay. And so we use the flux lines to describe how the magnetic field would look if you could see them. Now, obviously, we can't, but it's a way of visualizing the interaction between different magnets, between different kinds of magnetic materials. Okay, here we have a picture of a magnetic field around a single bar magnet. All right, it would be like if we took a bar magnet and just kind of stuck it out here in space. All right, north end over here, south end over here. The magnetic field around this bar magnet would appear almost identical to this magnet here. Now, why would we picture it this way? And why do we have the arrows on the flux lines in the manner that we do? Okay, give me a moment to set something up here. I love moments in video land. They take a fraction of a second. I actually took several minutes setting this up. Okay. Here we have a bar magnet. Over here is the North Pole. Over here is the South Pole. Now, if you'll recall, the reason that it is that way is if I were to allow it to freely to rotate, it moves around so that one end ends up pointing toward sort of the geographic North Pole, and the other end ends up pointing toward sort of the South geographic pole. This isn't doing this because I've got other interference in the room right now, okay? But you did notice it start to swing. That's where the terms North and South Pole come from, okay? Now, this right here is a miniature compass. But as you can see, it will react to the magnet that's down here, okay? All right, another way to see that, all right, you see how if I flip this around, it's creating a change in the compass here, okay? Compasses are just tiny magnets, all right? And a compass will always align itself to an external magnetic field that is influencing it, okay? So right here, this compass is aligned so that its north pole, the white side, points to the north pole of the magnet, okay? Now what if I put a different compass somewhere else? All right, now notice that that compass is not pointing exactly the same as that. And that's because this end, the North Pole of that compass, is attracted there, but the South Pole is also attracting it somewhat. And so notice that this is kind of at an angle to that. All right? Something's up with this compass. Its polarity must be reversed. Okay, so I'm not going to use it. Aha, there's one. Now notice with this one, notice how the red part of it is in the opposite direction. I don't know if you can see that, but the red part is pointed toward the South Pole over here. Okay, another one. Okay, notice that if I point it out here, notice it's kind of pointing sideways. It's not really pointing at the compass. Okay, notice with this one over here, it's pointed at the compass, but if I move it, notice it changes its orientation. So it's trying to point to the nearest pole. Okay, so no matter where I put these, if I were to put a whole bunch of them, that's a bad one too. If I were to put a whole bunch of them around, as you can see here, bad one. Okay, they all mirror that diagram that I had around the single magnet. If I were to fill this space with all these magnets all around here, fill it, absolutely fill the space with magnets, you notice that if you were to draw lines through the compass needles of each one of the compasses, they would create that diagram that I had shown you just a moment ago. Okay? So, what happens when I have two magnets? What does the magnetic field look like between two magnets? Well, it's pretty obvious that, it can go from one and then flip around and you see it goes to the other. All right. And notice that it's following an arc out here. Okay. And so the magnetic field that's in this region right here between them represents how these two are attracting each other. Flip this around and watch what happens. The compass comes out. Notice that it's still attracting here. But then we get to a point about halfway in between. And it flips around. Okay. Now notice if I move it off to the side here, notice that it's pointing, it's repelled by both of them. Okay. So the south pole of this compass, in other words, the white part, you see how it's getting changed? All right. And that means that the field must be doing something like this inside it. To visualize that in a picture, we use the following way to see it. Okay? So, a north to a south pole, the lines of force go between them, go directly between them. They connect them. And this shows that if you were allowed to freely move, they would move toward each other. They would pull toward each other. The south would move opposite to the direction of the field. The north would move in the direction of the field, and they would join together. Over here, you have exactly the opposite. You have part of the field going into the south over here. You have part of the field going into the south over here. Where these lines are coming from? The other end of the magnet. All right, so this one's lines are coming from the North Pole down here below. This one's lines are coming from up here, up on top, the North Pole on top. lines that are kind of acting in the same direction will not cross, they will not interact. And so you can see how this is creating kind of almost like you could visualize it as if it were a type of spring pressing these two apart. Okay? Direction for flux lines is always from the north toward the south, out of a north pole into a south pole. Now, if a field diagram is drawn to any kind of scale, the distance between the lines will also indicate a level of strength for that field. All right, the magnetic field is stronger where you would have lines of force closer together. Notice that out here, these lines of force are separated, but in here they're relatively close together. So this is indicating a strong field. Notice that the field in here is strongest right at the poles. I could draw more in here, but it would get confusing. This would be a point where essentially the field is zero because it's going all away, all in all directions equally. Okay? So if you know that you've got a magnetic field happening, and if you were to put a compass in that field, you know that the compass or any other magnet, could be a regular bar magnet, will attempt to align itself with a magnetic field that's external to it. Okay? So that this will go in the direction of the magnetic field lines. So if, let's say, for some reason in this video, I had a magnetic field that was going vertically, straight up, okay? And that's the direction the flux lines would have, straight up. If that were the direction and I were to let this magnet go and it were to levitate in this field, you would see it align, boink, like this, because the lines of force come out of the north, they go into the south, and since that's the direction of the magnetic field lines, that I'm describing in this space, this would align itself that way. If, on the other hand, the magnetic field were horizontal and the magnetic field were directed this way across your screen, we would see the compass go like that. Okay? The compass would align itself in the direction of the magnetic field. The magnet would align itself in the direction of the magnetic field. One of the things that the early scientists didn't know about was the structure of the atom. They didn't know about electrons. They didn't know about neutrons and protons. Okay, it wasn't until much later that they figured that out. Problem is, we're already using electricity. And what is electricity? The motion of charged particles. As scientists were doing demonstrations of electricity for the wider public, for people that wanted to know about it, this was before the era of YouTube, they would put together these really wonderful demonstrations and hold lectures, public lectures. You had to buy tickets to get to them. Okay? At one of these lectures, a Danish scientist by the name of Hans Christian Ørsted noticed that somebody had left a compass on his demonstration stand, and it was near his electrical equipment. And he noticed that every time he turned on the electricity for the demonstration to happen, the compass would move. Weird. Why is the compass moving when the electricity is happening? He turned the electricity off and the compass would go back to pointing the way it normally would point. Turns the electricity on, get a change. Turns the electricity off, goes back to the other way. All right. This inspired the question: is there a connection between electricity and magnetism? They really didn't know what might cause it, but they could see something was happening. He went back to his lab, did more extensive tests, and noted that every time he got an electric current in a wire, he would produce a deflection in a compass. So obviously there was some sort of interaction between the electricity in the wire and the magnetism of the compass.
This inspired Sir Humphrey Davies, an English scientist at the Royal Society in England, and his lab assistant, Michael Faraday, to begin exploring this more extensively. And Michael Faraday took it to the nth level. And it's why we credit much of what we understand today about electromagnetism to Michael Faraday. Interestingly enough, for us here in America, Joseph Henry at the Albany Academy, yes, our Albany Academy across the river over in Albany, New York, um, discovered similar principles to what Faraday discovered. And basically, because they're on the opposite sides of the Atlantic, their publications happened about the same time. And so they're kind of credited as both making the discovery at the same time. It's just Faraday did more with it than Henry did. Okay. And so Faraday gets a lot more credit. Plus, he was a really good friend of a young mathematician by the name of James Clerk Maxwell. And Maxwell was the one who put the math to everything that Faraday was visualizing and thinking about. Okay. Faraday then does an interesting experiment. Okay. Faraday's setup was basically this. He took a wire, all right, and he had it connected. He, imagine it going down through the bottom of my lab stand and over to the side over here and connected to an electrochemical cell, a battery. Okay. It comes up and he makes a circuit out of it. And so he has a switch and he throws the switch and he has current flowing through the wire. And so he's going, okay, if I take a compass, now I don't have electricity flowing through this wire because in order to do this, you have to have a huge amount of current and it would melt the insulation on the wire, and I'm not going to do that. Okay. But what he did was he took a compass and he had the electricity off and he would turn the electricity on and he would wait to see what the deflection of the compass would be. And one of the things he noticed was he took many compasses and he would circle the wire with those compasses. And what he found was that when the current flowed, all the compasses would point kind of in a circle around the wire. So they're all pointing to the next. It was as if they were all connected, one in line with the other. If you can see this, you notice that these aren't. So I don't actually have current flowing in this wire. But he said, okay, imagine that they are aligning themselves to the flux lines of the magnetism created by the electricity flowing through the wire. And this is what convinced him and a lot of other folks that we're now talking about an interlinked force. It's not just electricity and magnetism separately, it's the two of them together. Because if you turn off the electricity, these all go back to being oriented in Earth's magnetic field. Okay? Turn the electricity on, they reorient, and they orient so that they are circular. They don't point toward the wire, they don't point away from the wire, they point around the wire. So you get this kind of circular orientation of the magnetic field around a straight wire.
So that experiment that he did, along with several others, was the definitive uh, empirical evidence that electricity and magnetism were interlinked. And so now we start talking about electromagnetism. Okay? Any flow of electric charge through a conductor creates a magnetic field around that conductor. Now, to visualize this, I now have to be able to visualize in 3 dimensions on something that is essentially only 2. Okay? So we have the X direction, horizontal. We have the Y direction, vertical. And now we have to have the Z direction coming out of the board or going into the board. All right? So if I use this symbol right here, this symbol right here represents a vector coming out of the board or out of the page towards you. In the case of you, it's coming out of the screen towards you. All right?
Think of it this way. What is a vector? A vector is a quantity that can be represented with an arrow. If an arrow is coming towards you, what part of the arrow is closest to you? The point of the arrow. So that represents the point of the arrow coming out toward you. Conversely, if an arrow is going away from you, what part of the arrow is closest to you? Do you see? You see the feathers. All right. And so think of the X as the feathers of the arrow going away from you. All right. And so that's how we're going to use three-dimensional vector notation to talk about electromagnetism when we picture it on a two-dimensional sheet of paper. Okay?